Hi everyone and welcome to this last lecture of week 3, and today we want to talk about active and passive transformations. So the linear transformations were written like, let's say you have a v prime, you have some operator, let's say omega, and you have v over here. So this gives you a linear transformation, and so does, let's say, w prime is just w omega, or let's say this is another operator, omega prime. And these linear transformations can be seen as either active transformations or passive transformations. So first I want to show that what is an active transformation. So this active transformation will be given, let's write first active transformations. Let's say you have a vector space. Though they are abstract, but let's just try to draw a vector that is given by v. And what you do, you want to operate some operation on this vector, that is, let's say you have this v prime which is obtained from v with the help of an operator. And after you operate this, that is, you do this whole thing, this vector, let's say it will give a new vector, that is v prime, and let's try to draw v prime. Let's say it will give you this is v prime. So you can this is a diagram and this is not rigorously correct, but this gives you a way to see what is happening. That is, let's say this is a rotation operator, this omega. So if this is a rotation operator, it will rotate the vector. If it's a scaling operator, it can scale the vector. Let's say now you can think of omega scaling operation. So what will happen is that, let's say this is a scaling operation and this will just get scaled. Yeah, or it can be a rotation plus scaling and many things more, right? So this type of transformations are called active transformations. And the reason they're called active transformations, because here the vectors themselves gets affected by the operators. So this is an example of this active transformation thing. And now let's try to look at passive transformations. So when we talk about passive transformation, we want to particularly focus on unitary transformations. So let's say you have a vector v prime that is obtained from v with the help of a unitary operator, and you have this v prime bra is just u dagger v. And in our earlier lecture, that is the last lecture, we saw that this is just v. That is, the inner product is preserved, right? So we obtain these v primes through these unitary transformations. Now what we want to do is that we want to calculate the following. We want to calculate the following. That will be v prime omega v prime. In fact, this is something that is called an expectation value, and you will know more about it when we discuss this eigenvalue theory. But let's now let's just write it down as expectation value. And here we can see that these v primes were obtained via the unitary transformations, and this expectation value corresponds to this omega operator. So this is the expectation value for operator omega, and the corresponding state is, and state v prime. So if you just do it, you can see that this will be v, u dagger, omega, u, and v, right? So from here you can say that instead of affecting the vectors themselves, I can affect the operator. That is, instead of changing the vectors actively, why don't I change the operator and calculate the result? So this is what is known as a passive transformation. That is this one. So what does this mean? This means that if you transform this and denote it with lambda prime, omega prime, this is just u dagger, omega, u. So this, when the operator itself gets affected, this is known as the passive transformation. Now you might be confused that why we are doing this at all, right? It will turn out that both of this active and passive transformation will give you the same physics. That is, it will give you the same invariant physical information about a system. So let's try to see that in a different perspective. So we are going to adopt a example from quantum mechanics. So QM example. So in quantum mechanics there are two pictures. One, obviously there can be more pictures. We want to talk about two pictures in particular here. One is called the Schrödinger picture, another one is called the Heisenberg picture. So in the Schrödinger picture, let's denote it with 1, or say, so to say, the picture 1. Here what happens is that a state is denoted by a vector psi. Again, this is an abstract vector, and its time evolution is given by this following equation. Okay, and this is our unitary operator. Now an operator, let's say I want to know the energy, or okay, not the energy, let's say something else. Let's say I want to know what is the position of this thing, right? So there are two ways I can do it. That is, I just act with psi of t. It will give me x e to the power I h t psi 0. This is one way to do it. Another way is to use this passive transformation, and if you just, you see, this is not giving you a number, rather it will give you a if you think in terms of x as a matrix and psi as a column vector, it should return you as a column vector. So but this is not true for position operator. It's an infinite dimensional operator, and it's actually a derivative operator. But let's ignore that, and let's just think of this as some position that we can represent with matrix as well. So if you want to find the expectation value, that is, you want to take a number, you have to write it like this, and if you do that, you will have this thing, x e to the power I h t psi of 0, right? But here you can decompose this thing in terms of psi 0. So if you do that, that will be e to the power I plus I h t x e to the power minus I h t and psi 0, and you can call it as x prime. So in the end you will have psi of t x psi of t equals to psi of 0 x prime psi of 0. So here the states got affected, and here the states were not affected, rather the operator got affected. So you can think of it like as going to a moving frame, or so to say a rotational frame. That's how you can think of it. Because if I try to draw a picture, let's say this is some circle and one observer is seeing from the outside. Okay, this doesn't look like an eye. Okay, this is observer 1, let's say, and there is a vector, it's rotating, let's say. So this is like the active transformation, where there is an operator that is making the vector rotate, and this will correspond to an active transformation. And if you have some observer here, that is observer 2 over here, and now this whatever this observer 2 will observe is seen from a rotational frame, and instead of this operator omega, he will think that this omega is actually something like this. So this is not a very good picture, but it can give you some idea why this is called a passive transformation. But the main thing to keep in the back of your head is that both of this transformation will give you the same physics. And before we finish off, in the past lecture we said unitary operators are very important, and since we brought up the notion of QM here, so we want to see why unitary is important in physics. So again, we take QM example 2, let's say, and we're going to discuss the famous Schrodinger's cat problem. Oops, sorry. So the idea is that you have a box like this, and here you have a cat. Okay, it doesn't look like a cat, but let's say this is a cat. And you have some radioactive materials and some trigger that will cause this box to be get poisoned, and the cat might die or it may live. But the idea is that the box is obscured. That is, you have to open the box to see what is happening inside. So whether the cat is dead or alive can be represented as a wave as an vector, not a wave function, rather a wave vector. You can always call it a wave function, but for that you have to take the position representation, but we are not doing that here. So let's just call this thing as a cat vector, and there might be some probability where that is represented as C1 and this one. And let me explain to you what this means. This C1 will be a probabilities square root. That is, C1 will actually give us some probability whether it's dead. So let's call one as dead and the other one 2. Let's call it alive. These are two states. The cat is either dead or alive, or maybe there might be many things more. So when you compute the inner product, you will get this C1 squared times C2 squared, because one inner product with 1 is just 1, because these dead and alive states we are calling it our orthonormal basis. That means there is no overlap between them. So that's why this thing will give us this C1 squared C2 squared, and it will be equal to 1, because they will represent probabilities, C1 squared and C2 squared. So these two things represent probabilities. Right? And this is also known as the Born rule. I should have written Born as capital B. This is due to a gentleman called Max Born, and this is most of the QM texts state it as a postulate, but you can actually prove it via the Gleason's theorem, but let's not go into that. It's another subject for discussion. So using this Born rule, what should this C1 square and C2 square should represent the probabilities of the individual states. So if you want to know whether the cat is alive or dead, let's say I want to know the probability of the cat being dead, so this will be just C1 squared. If I wanted the probability of, so let's write it as prob of dead, probability of dead or death, and this is just probability of being alive. This will be equals to C2 squared, right? And the sum of all the probabilities are 1. And if you recall that unitary transformations preserve inner products. This is from the last lecture, right? And now we have our Born rule that says if you have a state psi that is written as a linear superposition, let's say it's an n-dimensional vector space with CII, where the CI squares will represent some probability. If you combine them, okay, let's not use this symbol or abuse this symbol. So if you combine these two, let's call it 1, let's call it 2. Combining 1 and 2 gives you that this sum over I Ci squared is just 1. That is probability conservation. And unitary transformations are the only type of transformation that conserve probability. So that's why it's very important that in a physical system, if it transforms in a time or something like that, and you want to get something invariant out of it, it should be unitary. So this will you will know much of this more when you take a quantum mechanics course. But this will be it for today, and that's the end of week 3. And from next week, what we want to do is that we want to solve the eigenvalue problem. That will be a very interesting thing when you want go to quantum mechanics, or even you will see these eigenvalue problems in differential equations as well. So from next week we will focus on the eigenvalue problem and how we can deal with eigenvalues, eigenvectors, diagonalization and all that.